Yeah, today we're going to talk more about chords and another special relationship that exists when two chords intersect in a circle. And so I'm going to use my sketch pad to show you. I have a circle here. And one of the chords that's going to be involved in this relationship is a diameter. Remember, we know it's a diameter because it goes through the center of the circle. It's all inside the circle and it touches both sides. And then we have this special relationship when we have another chord intersect the diameter in such a way that they're perpendicular. And so if they're perpendicular, you know that they're making right angles. And so I went ahead and I measured these angles. So I specifically measured angle AEF, this one right here, actually where the letter E is. And you can see that's 90 degrees. And so the relationship is that if I have a diameter or a radius, because this side doesn't really matter. If I just had this radius, this relationship would still exist. If I have a diameter or a radius that intersects a chord so that they're perpendicular, they make a 90-degree angle, then that chord, so this red chord, gets bisected. It gets cut in half. It gets cut into two pieces that are equal. So I measured these pieces of the chord, so DE and FE. And you can see right now, with that angle being 90 degrees, those two parts of the chord, DE and FE, are the same size. And so I have an animation here where I can move this red chord back and forth. And you can see that the angle will not change. The measurements will change, but they'll be the same as each other the whole time. So let's do that. So I can stop, and they're going to be the same length. And I can stop again, even to where it's almost a diameter, and they'll be the same length. And so it doesn't matter as long as that chord and that diameter are perpendicular, making a 90-degree angle, the two pieces of that chord, the red one, are going to be equal to each other. And so just another special relationship that exists between segments in circles. So this is how it will look to us when we're doing practice. Like I said, it doesn't have to be a diameter. It can be a radius, or in fact, like in this case, it could be part of a radius. It's part of a radius because this segment originates at the center of the circle. This segment's a chord. It touches the circle twice, and they're perpendicular because they make a right angle. So that means this part of the chord and this part of the chord are congruent. And so if this part right here is 17, the other part x is also 17. And so here's one that looks different, maybe a little more complicated, but I have a diameter, and it intersects a chord, and I know they're perpendicular because they make a right angle. So that means that the two pieces of that chord are equal, so that x is 2. And so just another way to look at it, again, I do have a diameter, and I also have a piece of a radius, like I did in the first one, and that intersects this chord, and they're perpendicular because of the right angle there. And so again, that means that these two pieces are congruent. So x is 16. So it would be really nice if those were the only types of questions we were going to do, but we all know that it's we have to add a little bit of a layer of complication. And lo and behold, when we have right angles, what we'll end up seeing a lot are right triangles, just like we saw in the last lesson with tangents, and what we saw in the last unit when we talked about right triangles. And we can use the Pythagorean theorem here when we want to find a missing length. So in this picture, I have a radius, I also have a diameter, but the radius right now is what I want to look at, and it intersects this chord and makes a 90-degree angle. So what we know based off the sketch I showed you and the last page, that since this radius and that chord are perpendicular, they make a right angle, that that piece and that piece of the chord are the same length. So I can say that that is 13.3. And now it looks like I have a right triangle. I got this right triangle with two sides, one that's 13.3, one that's 9.7, and I want to know what the hypotenuse is. So I can use Pythagorean theorem. My hypotenuse is x, the thing I'm looking for, it's across from the 90. So I plug x in for C, 13.3 and 9.7 go in for A and B, and now I'm solving like we have been now for quite a while. So I can find out that the hypotenuse is 16.46. The other thing that's cool here is that hypotenuse happens to be, and let me get rid of that, the hypotenuse in this triangle also happens to be the radius of the circle. And so now if I wanted to, I know the radius, I could find the diameter. I know the radius, which is also the same as this yellow piece. So this yellow piece is also 16.46. I know this part of it's 9.7, so I could find how long that segment is. So this really helps us find a lot about what's going on in a diagram. So let's do another one. I have this piece of a radius. It's part of a radius because it starts at the center. And I have that chord intersecting to make a right angle, so I know that that part and that part of the chord are congruent. And so therefore, I'm going to make that, that's probably good. I can put an X on this chord. So now it looks like I got a right triangle where I know the hypotenuse is 11.9, one leg 6.7, the other leg is X I'm looking for. I can use my Pythagorean theorem, and I can figure out how long that piece of that chord is. It's about 9.83. And so that means that both of these pieces of that chord are 9.83 long. If we wanted to know how long this green chord was, we could just add 9.83 to 9.83. So I want you to pause here, and I want you to try this one on your own. I didn't have you try one on your own on the last page, so I want you to try this one on your own, and then press play, and I'll do it for you. So again, I have this time I have a whole diameter, and that whole diameter intersects this chord, and I make a right angle. So I know that this piece of the blue chord and this piece should be the same. So I again can put X right there, and I have a right triangle. I know the hypotenuse is 10.3, one leg is 5.5, one leg is X. I'm looking to see how long that is, and I can just plug into the Pythagorean theorem. And I find out that that piece is about 8.71 long. So I have one problem for you that I'd like you to do on your own, and then if you have questions about this lesson, make sure to ask me in class, and we'll discuss it.